Now, what we're going to talk about now, we talk about the joint distribution. We talk about the marginal. We talk about the independence. We talk about bivariate transformation. I think all very important. All very important. And moreover, you need to know marginal distribution to understand bivariate transformation, because they're almost the same. Now, what do we call the joint distribution? This is when you have, we talk about the continuous form. Or continuous distribution, or continuous form, yeah. In the previous chapter, from chapter 1 to chapter 3, we've been talking about univariate. Now we're talking about the multivariate. When you have more than one variable, you want to look at the joint distribution. And one good thing about this distribution is that it's good to write papers. In fact, if your area of research is on distribution theory, you can write as many papers as possible in a year. Yeah, I think I have a call. No, Alexa, no. Okay. Okay. It's all right. Okay. Okay, now we have this, okay? Now, for the joint distribution, you can have negative infinity, positive infinity, depending on the conditions. You can, assuming we have 2, x1, comma, x2. Now, this is where the catch is. You can differentiate with the closest one. You can start your differentiation with x2, the x1. Okay, you differentiate the most recent. Okay, I'm used to x and y. Okay, sorry, x1, x2, x, y. So now you can differentiate with respect to the y, the x, or the x, the y. Either way. Yeah, the limit. Then this is going to be the limit of y. This will be the limit of x. Okay, depending on how you set this up. Now, that's for the joint distribution. You can have more than one. You can have like 4, 5, 6. I think there's an example that we have like 4. So we're going to look at that. Now, this is for the joint. If you have that of the marginal, okay, your f of x. For you to marginalize something, it means, say for instance, we're in a room, or we have Sam, we have Sach, okay, and I'm giving you this box. 2 of you to share. And Sam, Sach, 2 of you. And then I'm giving you this box, okay? You run away with the box. Yeah, you run with the box. I mean, so you marginalize Sach. You didn't give him his own portion, okay? So now, that means you have x and y. We have 2 variables, right? So you want to marginalize x. You want to get the distribution of x from x and y, okay? So you're going to use the limit of y. This is going to be the limit of y. Don't forget, limit of y. So it's now going to be the joint distribution, the y. The joint distribution, the y. Okay? Now, to make you understand it better, let me put it in a better form. For A, you have for x, you have a less than x less than b. For y, you have c less than y less than d. Let's use this. So for this, you have c, d, you have a, b. You understand? So here we have c, d. So now you are using the limit of this of y for x. So the same way, if you want to marginalize y, you use a, b, f of x comma y dx. So it's considered you are changing it. So this is what we have. Now, before we proceed, and we have independence, just the same rule for independence. If the joint distribution of x and y can be separated into two, as in the multiple of the two. So it's called joint independence. Or let me just put it this way: if you have your fx comma y, it can be expressed as g of x times h of y. This is called independence.
That means this joint period can be separated as integral a to b f of x dx times integral c to d f of y dy, right?
Not f of x, it will be the joint distribution. Yeah, you can go write it. Let's see.
So in the marginal we can distribute into two independent ones. The joint distribution is independent.
Oh, okay, yeah, okay. Yeah, write it, but I understand what you're saying now.
Either x, I will use x and y. X, y, f of x, y, dy, dx is equal to x, f of x dx.
Yeah, exactly.
This is the right.
Yeah.
Okay.
Yeah. So this is now following this form. This is now going to be your g of x times g of y. This is the form. So the purpose I use this is that it can be in discrete or continuous form, either way. So just know that it can be expressed as that. Now let's look at some examples. Yeah, before we move on, let's talk about conditional distribution. Conditional distribution. Yeah, of course, there is always, always, especially when you talk about this Bivariate transformation. When you talk about independence, you from India. I think India and Nigeria were almost like families. When did you get your independence? Oh, you are our senior. We got ours 1960. Yeah, but we became republic in 1963. Let's say 1960. Yeah. So you are 13-year-old. You are our senior. Mother India. What about you?
1948.
Sri Lanka? Just 1 year. So you guys, did you fight to gain independence or what? You fought together. You fought the British? I knew we are being colonized by the British. Yeah, so it's almost the same time. Yeah, Mama Gandhi, of course. Everybody knows Gandhi. So it makes sense, you know. But over time, I think India, you've been developing in terms of technology a lot. But unfortunately, we are all being affected by the kind of leaders we have. That's the problem, you know. We have a lot of resources, but at the same time, we are not enjoying it. Okay, let's go back to statistics. That is interlude. Now, here, if you have fx given y, this is fx comma y divided by what? Fy. Now, this is easy. This is called
conditional, right?
This is conditional. This is conditional.
Conditional distribution.
Conditional distribution. and you're going to use it a lot. This is the joint, and this is the what? The marginal. If you look at chapter 7, is this chapter 7? Yeah, there's something we did. When we get there, I'm going to explain it. Yeah, when you want to talk about Bayes, beta exponential, I think beta exponential distribution, the Bayes we have, but there's something we need to understand on that. Each of the distributions have their conjugates. Normal is normal to normal. Beta, what distribution do we use? I think exponential conjugate is better. No, when we get there, we'll talk about it, but they use this a lot, okay?
Yeah.
We talk about the marginal, we talk about the joint distribution.
The base estimate, we don't have to look for the marginal distribution.
Yeah, exactly. That is like a shortcut.
In 2020, he asked to find the marginal in the base distribution. The part we have to find the.
Really?
Yeah, separate distribution and also the second part is to find the.
Just to show you how to integrate.
Yeah.
Okay, now, this is it. Just to show the relationship that exists between the marginal and the joint distribution. Now, do we need to look for examples to show what we're talking about? Can we just look for one example?
Yeah.
Okay, I think I have an example here. Yeah, I think I have one. You have example. You have f x comma y to be equals to 6x y squared. Yeah. Yeah, the limit is 0x less than 1, 0 less than x less y less than 1. So the question is, find the joint distribution. Okay? The joint distribution or integration. So this is the joint. You want to find show that your fx comma y equals to 1. Okay, that is a PDF.
Yeah.
And then you find your f of x. See the probability that x plus y is greater or equals to 1. So these are the things we need to show. Now, this is what we have. Let's do the first part.
Both of the limits are same, right?
Yeah. So we want to show that this is a PDF. So that means you integrate with respect to the respective limit. You have 6xy squared. You can, let's use the x to y, right? Either way, it's still going to be the same. So for the first one, this is going to be 6x squared y squared over 2, 0, 1. The what? You still have your dy. So when you plug in, you have 1, 0. If you have 1, 2 here, 1, 2 here, 3, right? So here we have 3y squared dy. Now, if you integrate these two, here you have 3y cube over 3, 0, 1, which is what? 1. So that shows it is a PDF. It is a PDF. Now, for the B part, find the f of x, which is the marginal distribution. Here, you don't have any problem with the limits, since they have the same limits. So here we have 6xy squared. The what?
Respect to dy.
The y, good, yeah. So if you integrate, you're going to have 6xy to the power of 3 over 3, 0, 1. You have 2, which is 2x.
How do you get 2x? 2x, right?
Yeah.
I don't know what C. How to do that.
Yeah. So here we have C. The probability of x plus y is greater or equals to 1. Recall that we have 0 less than x less than 1, 0 less than y less than 1. That is, the max should be 1. Okay? Should be less than 1. Now, your x plus y is greater or equals to 1. That shows your x is greater or equals to what? 1 minus y.
It's x plus y is greater than x.
That means your x is greater or equals to 1 minus y. So for this alone,
How did we select the first condition? X plus y is greater than x.
yeah, this is the given in the question. Okay, you just have to change it, rewrite it such that you have this, and you can also plot. Okay, you can plot to show that this is to show this. Okay, but you do it this way. Now, if you have the limit now, the first one, I'm coming, 6x squared y. Now you have the x, the y. So the limit of x means greater or equals to this, means from 1 minus y to what? To 1.
Okay, 1. Okay.
To 1. So this is what? 0 to 1. Your y is not being tampered with. So this is what you do. Importantly, the one with variable, let it come first. Okay? The one with variable, we have a lot of probability. I think if I see another example, I'm going to show you. There's another one that you have 2x plus 3y greater or equals to 6. You just say that, okay, 2x equals to 6 minus 3y over 2. Sorry, greater than. So you have x greater than 6 minus 3y over 2. You understand?
That means the lower limit of x should
Yeah.
be 6 minus 3y by 2
To the
given limit.
to the given limit.
Given upper limit.
Yeah. There's an example like that probably in the notes. Yeah. So now here we have this 0, 1. Okay? Now let's integrate this. Here we have 6x. Oh, sorry, it's 6xy squared. Yeah.
So the probability can be written as the integration.
Yeah. So here we have 6xy cube over 3. The what? The x. The y. Oh shit. X come first. 6x squared y squared over 2. 1 minus y to 1. And here we have this gives 3, right? 2 here 1, 2 here 3, right? X squared is going to be what? 1 minus y squared y squared. You with me? Minus, just bring this 3 out. Minus y squared. Okay? The y. Let's break this down. So here we have 1 plus y squared minus 2y squared minus y squared. The y. Look up. Am I on the right track or mistake? Yeah, you do it your own. So let's see. So here we have y squared plus y to the power of 4 minus 2y cubed minus y squared, all the y. This cancel out this. You have 3, 0 to 1, y to the power of 4 minus 2y cubed, the y. Now you can now integrate this, y to the power of 5 over 5 minus 2y to the power of 4 over 4, 1, 0. And here you can have 3, 1 over 5 minus 1 over 2. And here we have 3, 2 minus 5 over 10. There you have minus 9 over 10. Do you all get the same?
Minus 9 better.
Yeah. Oh. No. There's a mistake somewhere. Let me identify. Yeah, that's true. It's probability. Let's check. So here we have 2 here 1, 3x squared, y squared,
Plus 9 over. Plus 9.
plus 9. Then how did I make mistake here?
The opposite.
I think you
1 over 2 minus.
you didn't take the upper minus lower. You made the lower minus upper. I think. Top or something.
Is this? Is it? Is upper minus lower?
First line. Just check. You made you select the look at that the first step.
Okay. Yeah. Yeah, look at that. Thank you. Thank you. Thank you. And one thing about mathematics is that it's easy for you to identify your mistake. Because now, probability can never be negative. That's true. So now, let me just give an example on conditional. There's an homework given on conditional. Now, let me ask you this. Can you do this? If you have that, yeah, if you have x and y to be independent, then find f x given y. Yeah, try it. X and y are independent. What is f x given y?
Okay.
The marginal of
It's marginal of what? Yeah, that's true. It's marginal of x. Shit. Yeah, my laptop. So here we have fx times fy, which is the joint fy. So you have this. Now, let's move straight to, yeah, there's a question I'm seeing here, which can be of interest. Let me try to talk about it. Okay, let's clean this. It's on MGF. Let's just talk about this and we move to bivariate transformation. You still have covariance correlation. We can't finish chapter 4 today. You still have covariance correlation and their properties. Chapter 4. We can't. We still have some other things to do. It's too much. What I'm just doing is the basic things you need to know. Now, look at this. Okay, let me quickly just give you this first. Look at this example. On MGF, I'm going to give you two examples. If Z equals X plus Y, okay, then MZ of T equals to MX of T times MY of T. Can we show this? It's easy, right? So that means here we just have here we have e to the power of tz equals to what? E to the power of tx, okay, times e to the power of ty. And here we have e to the power of tx times e to the power of ty, which is plus rule of indices, okay? And here we have e to the power of t x plus y. So here we have what? Mx plus y of t. And what is x plus y? Mz of t. You have it as mz of t, or you can have it separately. Okay, this I just showed this is equals to this. Or you can just split it. You can what you see what I did here? Yeah. I just showed this. Now let me show you something else.
Hey, let me ask you a doubt. The very first question, the very first line itself is a proof, right?
Yeah. I prove it the other way around. Let me show you. I only show this equals to this. Here, if you have this, okay, you want to show this, right? This, you want to use it to show this. You can have the mz of t to be equals to e, okay, e t x plus y. I want to use it to show this now, okay? Mz of t is e t x plus y, which is the same thing as e tx, okay, plus ty, which is e tx times e ty, which is mx of t my of t.
If x and y are independent.
There's nothing like independence here. It's not compulsory they're independent. Yeah, they should, because we don't have any, even there's nothing like independence because we don't have anything like covariance here.
How do we go from step 2 to step 3?
From here to here, it's just indices. If you have 2 to the power of x plus y, it's the same thing as 2 to the power of x times 2 to the power of y.
Okay, that means in this case it should be independent.
Yeah. No. If you talk about this in the indices in high school, it's just rule of indices. A to the power of, yeah, I only use the rule of indices. Now, this is the main question I have for you. So you want to use what we did here. Now, the question says that x is normally distributed with mean sigma square, and we have your y to be normally distributed with mean, okay, tau square. Okay, and find the distribution of z. Show that, yeah, z is normally distributed as mu plus this Can you do this? Just using the same rule we used there. The same rule we used. I want you to try it.
Is that a single express right?
Come and try it. Or Sash, come and try it. Come and try it, huh?
I think yeah.
Come and try it. Just give it a try.
It's provided the result is equal to express right?
Yeah?
Yes. And then
Yeah. Do you want to prove the MGF? You are going to use the MGF form.
MJ.
Yeah.
You have to prove it by MJ.
That is the shortcut. You can't just prove it using this method. It's going to be a long way. You see, there are two ways we did this. When we use, just like the normal Bayes, normal distribution, I think you can use something like that. But the best way, this come out in the, I think, in the first semester exam. Yeah, number 1. I think so. Question number 1. Now, this, you've gotten this, z is x plus y.
Yeah.
Okay? What is mx of t? Or let me put it this way. We've shown that mz of t is e tx, right?
Z. E raised to TC.
Tz. No, I want to add everything. Okay, either way. Equals to e tx plus ty. Right?
Yeah.
Now, which is the same thing as mx of t dot my of t. Now, it is in question number 1, I remembered. Now, we have this. X follows normal distribution. The mx of t is exponential mu t plus sigma square t square over what?
E raised to mu t plus half.
Over 2. Yeah. The same way for the second one, my of t to be equals to e plus tau square t square over 2. So now, to get mz, which is mx of t, my of t, which is exponential mu t plus sigma square t square over 2 multiplied by the exponential tau square t square over 2. Don't forget the rule of indices. If you have the same base, you can add the powers together. So here we can have mu t plus tau t plus sigma square t square tau square t square over 2. Right? Now, this is the same thing as t mu
plus r t square sigma square plus cos n.
okay plus what? T square sigma square tau square divided by 2.
Yeah, this is
So which follows what? Normal.
m plus r
This is the mu
plus r
plus r, comma what? Sigma square plus tau square.
If you use the bracket, we can do for a long time.
Yeah. It's going to take a lot longer time. I remember in the exam, she said, just use MGF.
Yes.
She said it.
Yes.
So, just use MGF, and it's easy. So once you said MGF, I pick. Sometimes when you're in the exam, you only need a clue. If you know what you want to do, but probably you just need hints to get what you want to do right, and then you're going to get it. But if you don't get the hint and you leave the exam more and you remember, oh, this is so easy. Now, bivariate transformation. Interesting part. Bivariate transformation.
Yes.
You also want to go to the restroom? Let me pause. So now, but for the bivariate transformation, just like you have two variables, you want to transform to like a new variable, okay? The first one I'm going to talk about, I will use that of Poisson distribution. You have a Poisson distribution, or let's use this example. Do you have any example with you there? Although I have some countless number of examples. Okay, let's talk about the discrete case. Okay. We have f of x given theta. Okay. We have x follows Poisson theta. Okay. You have y also follow Poisson lambda. Okay. And you have find x plus y, right? Yes, find x plus y. So addition of the two distribution. Now to do this, the first thing you need to do is, what is the joint distribution? Given that they are what? Independent. Okay? The condition is very important. So here you have f of x and f of y. So we have exponential minus theta. You have to find the joint distribution first.
Okay.
Theta to the power of x over x factorial. Yeah, that is why you can multiply, you are given two separate distributions. So for you to multiply them together, they must be independent. So that's the first condition we're talking about. Now, here multiply by exponential minus lambda to the power of y over what? Y factorial. This is f x comma y. And now let u to be equals to what? X plus y. You see, to me, I find this thing very interesting. Once you are able to get your joint distribution, you get your joint distribution. That's number one. Okay? Then, what is u? What is v? If you are able to get your u and v, make x subject of the formula, make y the subject of the formula, you get x and y. That is the transformed variable you need. And after that, you find the Jacobian. Sometimes it can be only 1x, 1y. Most times it's like that. Sometimes it can be 2x, 2y. That is, you're going to have like two Jacobian. But most cases, you only have one Jacobian. So plug in the value of u into the x in form of u and v, y in form of u and v, and multiply by the Jacobian. That's all. That's just the summary. It's good to summarize, but to actualize the summary is the problem. Now, let's do it. Let u to be this, and you can say v is x or v is y, either way. So let v to be what? Y. So let's get u. No, we've gotten y now. Y equals to v from here. Right? Now, what is x? X is u minus y. Right? That means x is u minus v. You see, what you need, if you are given this condition, you only need to get what is x, what is y. So any value given to you, let it be equals to u. Anything you want to find, let it be equals to u. Immediately I do this question, we have like a lot of questions on this. And we are going to do that of the past question for you to see what I'm talking about. Let it be equals to u, okay? Then you can now get your v from it. But sometimes you'll be given, find the distribution of x plus y and something. You can be told. Then the first one is going to be u, the second one is going to be v. But let's see.
How to select v?
How
to select v? It can be x or y?
Yeah, it can be x or y. It can be x or y. Are you okay with this?
Yeah.
Now, let's proceed. Now, let's form the Jacobian. Now, for you to form the Jacobian, the x, the u, I'm not going to write the derivative. The x, the u is going to be what? 1. The x, the v is going to be what? Minus 1. Let's go to, you get this, Sam?
Can you repeat it?
Can you write the equation?
Okay. I just like to do it very fast. Yeah. The x, the u, that is the first variable. The x, the v, that is the second variable. Now here you have the y, the u, the y, the v. So now the x, the u, if you differentiate this with respect to u, you have 1. If you differentiate this with respect to v, you have negative 1. If you differentiate this with respect to u, you're going to have what? 0. With respect to v, you have 1. So what is the Jacobian? 1. Let me clean this. Are you okay? Yeah. So now, let's plug in. Now you have f u comma v to be equals to x to be equals to what? What is x? U minus v comma y equals to v times the Jacobian. That's it. Mm.
U is expressed where?
Hmm?
U is how did you get this?
Yeah, this is the general form. What you just want to do is that you want to plug in x to replace u minus v, where you see y, plug in this. Okay? Now, we are using the joint distribution. Even this should be, I think this should be x comma y. Okay? You have x, f, x comma y, u comma v equals to this. Okay? Now, the joint distribution is exponential minus theta. Theta to the power of what?
This one is xy, right?
Yeah.
That's what I meant.
Theta to the power of what? Theta to the power of, you with me?
Minus v.
No. I want to plug in x and y into this equation.
X and y into this equation.
So you have u minus v over u minus v factorial multiplied by exponential minus lambda, lambda to the power of v, which is y, over what? V factorial. And here we have exponential minus theta plus lambda. Combining these two exponential together. Okay? Theta u minus v lambda to the power of v. Okay? U minus v factorial v factorial. You have this as the joint distribution with respect to u and v.
I think this will be after this, right?
Then you find the marginal. Okay? You find the marginal distribution, which is marginal of u. So,
This is joint PDF, right?
yeah, this is the joint PDF. And we have exponential minus theta plus lambda. You can introduce your summation, okay? Theta u minus v lambda v over u minus v factorial v factorial. Now look at this. There's something I would like to say about this. You have 1 over u minus v factorial v factorial. You know, when you have u combination v, what do you have? U factorial, u minus v factorial, v factorial. So what is missing?
Multiplied by U.
U. Okay?
Yeah. Oh.
So now, here you have exponential minus theta plus lambda.
Hey.
What is the rate of
Yeah, I thought you were somewhere.
Yeah, because I'm working on with marginal. So this is going to be with respect to v. I don't know the range of v. I think it should be from 0 to 1, 2. I mean, from 0 to, yeah. So, but it's with respect to v. Okay?
V, right? V.
V, yeah. So here you have,
Yeah, it's from 0 to
you have u, v. Okay? u, v, theta, u minus v, lambda to the power of v, divided by what? U factorial. Do you get it? That means you have this. So if you multiply this by 1 over u factorial, you have this again. So that means this divided by u factorial to give you this. You see, some of these questions, probably maybe you must have practiced something related to it. Yeah. If not, it's a little bit crazy. Yeah. So now, there's a rule we used in chapter 3 that I'm going to use now. Okay, now let me write this. So here you have exponential minus theta plus lambda, okay, over u factorial. What can you say about this? A plus b over n, which is summation A You understand what I mean? I don't like the way I bend. Now, if you have a plus b to the power of n, combination what? So n combination I, a to the power of I, b to the power of n minus I. And I think we have that now, yeah, right? So this is going to be my a, this is going to be my b. Okay? Yeah, I know. No, I just intuitive knowledge is what I need. So here we have lambda plus theta to the power of what? U. Now look at this. Exponential this to the power of u factorial. What does it form? Exponential lambda plus theta.
This last.
This?
Okay,
how I got this?
Okay, I understood from that.
From here to here is I put this out. So I have summation uv, let me theta to the power of v, u minus v. It's like binomial distribution. Okay, so this is like my ni, a to the power of ni, okay, b to the power of n minus I. This is my n, this is my I. So it is a plus b to the power of n. What is n? U. A plus b to the power of u. Okay. Yeah. So that means your x, the distribution of x plus y is exponential lambda plus theta. You can be asked, what is the distribution of theta x minus y? You can get that too on your own. There's one that is very important, and I think is on standard normal distribution to be independent. Standard normal distribution. Independent. Let me give you that, and you do that now. And after that, we can maybe call it a day, meet tomorrow, probably. Yeah, tomorrow, sure. Yeah, I just wanted to try it. Yeah. I wanted to try it.
Shall we do it tomorrow?
Okay. Yeah, I think so. Just for you to, let me just give it to you now. It doesn't take time at all, but let me see how fast you can be. No, we leave by 12. I still want to print something in the library. Then we have x follows normal 0, 1, y follows normal 0, 1. Okay? Follows 0, 1. And we have u. Okay, let me give you this easy one. X plus y. You have v x minus y.
Oh.
There's another one. That one is a little bit crazy. That one you have 2 Jacobian because you're having absolute value. Oh, don't worry. Don't let us talk about that.